Monograph, and this is a series that will start tonight and will run until the 5th of December. And we've got a really packed four webinars, with the fifth one being our usual open house webinar, which is great, and everyone gets involved in that, and it's a really great experience.
Yeah.
So this is our Soil Food Web, the living legacy series. So we look forward to all of you asking lots of amazing questions from our first webinar, and please let us know where you're calling in from. We love to know where you're tuning in from. I'll see if I can see some people coming in from Costa Rica, where we've just come back from running a brilliant workshop out there. We
Oh,
missed you out there, Iz. We missed you.
oh, I missed you guys too. It was not the same here without you guys. And I'm sure it's not the
Yeah.
same without me there either.
Uh, so so that's great. So without further ado,
Oh, I'm sorry, Nick. Should we do a quick reminder of the time of this webinars? Because this is the only one that is at this time. Then from the other ones are going to be an hour later. Is that correct?
that is absolutely correct. So what we'll do, why don't we go through each of the webinars before we get to our first one. So Daniel, let's introduce who we got for you today. So Daniel, please introduce yourself.
Hey everyone, thanks for having me. My name is Daniel Tyrkiel, and I'm the director of the Soil Ecology Laboratory here in the UK. So yeah, I think I'm going to stop there right now.
Well done, Daniel. Thank you. And we have Adam. Adam, please introduce yourself.
Hey, Adam Swan, also work at Soil Ecology Lab. I've been involved with making the compost and developing the kind of product that we make, as well as doing lots of other fun stuff.
Great. Well, we will hear so much more from both of you um, in a moment. So we're really looking forward to this one. This is going to be a great first kickoff for our webinar series. So Isadora, please introduce yourself.
Yes, thank you so much. Yes, my name is Isadora. I live in Spain. I work as a soil consultant. As you can see, I have very nice dirty fingernails that have been down with the soil. And yeah, I have my own company here. I'm also a soil food web mentor, and I love to do research. I love to work with farmers, and I'm really happy to be here. And I don't know, how about yourself, Nick? Would you like to give us a little introduction of all the amazing, wonderful things that you have done?
Gosh, that's very sweet of you. So yeah, Nick Padwick, co-hosting today with is Soil Food Web consultant and an instructor. I have my own business called Wild Soils. Have been a farmer for the last 40 some odd years, 43 I think this year. Gosh, wow, that makes me feel very old indeed. But very proud to be certainly part of the school and helping in the best way I can to support this amazing work that so many people are doing in this incredible community. So, why don't we just run through all of the webinars we've got coming up? So we're just tantalizing people with what the next webinar is. So today we've got the amazing Daniel and Adam of the Soil Ecology Lab, and they're going to sort of uncover all the hidden pieces within the paper written by Dr. Elaine and Dr. Russel Ingham. So that is going to be just fantastic. So we're looking forward to that in a moment. Who's next is?
That's right. Then we have also webinar 2, where we're going to have practitioners, the first soil food webbers that started, and they've been doing this for a long time. We're going to have Todd. Everyone knows Todd, Vivian, and Joe, and they're just going to talk about their experiences.
Fantastic. And then after that one, webinar 3 at 9 a.m. Pacific time on Thursday, November the 13th. We have Celine, who's going to examine all the natural defenses, rethinking soil as a strategic resource. So we are looking forward to spending time with her on November the 13th, Thursday. And then on our fourth webinar who's on our fourth one?
We have Nick Tomasini. He's been with us before, so we all know a little bit about him, and we'll get to listen to his story again.
Fantastic. And that's the following week on November the 20th. And then finally, this is the bit that we all thoroughly enjoy doing, which is our fifth webinar, World Soils Day. This is our community house party, where you get to join in. Everyone gets to join in, and we go into virtual little rooms, and we can start talking about all sorts of things to do with soil and compost and applications and whatever. It might even be past webinars. So that is going to be great, and we look forward to that.
Yeah, that's a great time. I really encourage everyone to join, because this is where we get to, choose our topics, and we have all the geeks around the world together in a very endearing way. Yeah? I consider myself a geek. I don't say it in a bad way, but there's some really interesting conversations, and there's a lot of knowledge sharing. There's a lot of funny things happening. So yeah, this is the time for us to create a little bit of a community and get to see each other a little bit more.
And for those of you who haven't been in this community house party before, we can go into virtual rooms and just spin around for a couple of hours, just going in and out of different rooms, talking about different topics. And as is said, there'd be some great people with lots of incredible information from their experiences. And that's kind of where you learn so much, guys, from what we're doing. Okay, what do we got next?
Should we get started, I guess?
Yeah, let's do it.
So this is webinar 1, Roots of the Soil Food Web. We're going to talk about the Ecological Monograph, and Daniel and Adam will be here talking with us for about 50 minutes. And then we're going to talk about the current offer that we're having right now. And we're going to have some Q&A. So everyone get to... Go ahead, Nick. Sorry.
Yeah, sorry. Yeah, just guys and girls, just bang in all of your questions into the Q&A, and we will cover as many of those as we possibly can at the end of the session. We hope to leave, as you can see, about 60 minutes of Q&A. You can always use the chat as well. Bung your questions into the chat. A few of us will be able to answer those as we go. I'm sure if Daniel isn't talking, Adam can start answering questions in the chat, and vice versa with Adam as well. And if there's anything and I can add in, I'm sure we can do that as well.
And please, questions related to the Ecological Monograph, and not life, not life crisis or anything like this. We're not qualified for that.
Not qualified for that. Not on this webinar, is.
No, not on this webinar. So without further ado, would you like to start, Daniel, or the presentation?
Sure, of course. Happy to. So thanks very much, everyone, for coming. I've been watching the hellos coming through the chat, and I can see that that our friends from the UK actually have come in strong to support us as well. This is our usual time in about half an hour. It's our usual time to have a Thursday call with Soil Food Web here in the UK, and we've got almost 100 of them on our list. So we get quite lively discussions almost on a weekly basis. There we go. There's Talis from Scotland. So Soil Ecology Laboratory. That's who we are. I'm just going to start with a short introduction of who we are. We are like the hub that Elaine dreamt of from the very beginning, and so we provide a biological product which is actually quite unique. Our goop is the only compost extract which is shippable and storable in chilled conditions, but it's storable for months. And then we provide hands-on training, so to complement the online training that the school provides for those of us who are tactile, and tangible, like to actually do stuff with their hands, we provide training here in Hampshire. Oh, and where we are in the UK. We're in Hampshire, about 20 minutes away from Basingstoke, on a farm right next to an RAF base full of Chinook helicopters. So whenever I'm not doing anything, a Chinook helicopter is flying above, going chop chop chop, Daniel, chop chop. So I know that I have to get stuff done. And then we also are a laboratory, and so beyond microscopy, we do quite a lot of other analysis, because we wanted to have a multiple viewpoint to what is happening with nutrition and biology within the plant soil ecosystem. And then this is what looks like in our little lab when people come to us. I wanted to, first of all, say thank you to Elaine. And so a little bit of background of how I got into this. I got into this from the perspective of permaculture. I did my permaculture design certificate back in 2014 with Jeff Lawton online. And through that course, I came across the work of Elaine. And I was hooked, because permaculture, especially in the UK, was kind of like a solution looking for a problem on broad scale agriculture. And Elaine's message was much simpler: just replace the chemicals with biology. Job done. And you can store carbon in the soil, and you can remove all the potential health hazards and all the side effects from food production, and have very good nutritional food. And so I was the first official student here in the UK when the school was not the school, it was the Environment Celebration Institute. This was beginning of 2017. That got me started. And I thought at first I thought that, I'm going to make it myself, or maybe there's already compost somewhere else being done which has got all the biology. So you can see the picture here. My daughter was nearly 7 years old when I was learning, so I was up at 4 a.m. doing the classes. And then I was interacting with the broader green waste composting industry. And so that magazine that you can see, that article was in 2018. I penned the article, and they printed it, centerfold, and I tried to convince them that there is future in biology, and you should be looking at it. That's a long story in itself, but then I knew that I had to show the industry, that this has got value, and so I started actually on a green waste site with the same one which we're on now. It's a farm with a green waste site. And then 2 months after I started, the largest storm in years happened, Storm Kiara, and blew my little straw house off the planet Earth. And so I had to stop. And then Elaine stepped in, and she was so helpful. I just pivoted to making thermometers for a year, and she said, "Yeah, let's help you, push you out there." And she helped to promote them, and we sold 123 of them all around the world. It was a lot of fun, but I wasn't making compost. But then Adam showed up in 2020, and we started making compost again. It was really great. So all of that, has really snowballed. And again, throughout all that time, first of all, Elaine was my mentor, because there were no other mentors. Elaine was my mentor. And so when I started the company, she also became an advisor. And so we had almost weekly chats on almost every Friday, where usually we would just geek out on experiments, because that's what Elaine does. She just loved all the science. She just would just absolutely geek out. And, it got to the point where we got recognized by the World Economic Forum and got this little award for the Smarter Climate Farmers. You can see me there, almost invisible in my dark blue. And then last year, we were so fortunate that we managed to have this trip where we brought Elaine and Carla, and we had 3 locations. One was Yo Valley, and then the other one was Sandringham Estate, thanks to Nick. Nick is amazing. And then the third one is a very close friend in Scotland, Phil Swire, on his Balmacewen farm. And we had so much fun together. And I was so happy to see Elaine, before she retires, because we always, just had virtual chats. So it was absolutely fantastic. And I'm so grateful because none of us would have been here without Elaine. And really, I mean, this woman, she just did all of it running on beer and hugs. You know, you've got to believe that, seriously. Absolute, just full of love. So we go to the main subject now, because there is a message here for us and for everyone. Elaine is a scientist, right? Scientists do science. Science is complex. Science is very accurate. And when we just make compost, because Elaine made everything very simple for us, when, you know, we just make compost because compost solves all of our problems, right? She makes it very simple for us so that we don't have to necessarily go too deep into it. But what we would like to show is all of these papers that have been created, they hold so much value, and it's oftentimes it's just hidden away and you have to search for things. And so we want to show you on the example of this most important paper that Google Scholar should be your friend. And Google Scholar is where you find a lot of the answers to the questions that you've got. And then what it does, it helps you arm yourself with facts, figures, and information when you are being questioned, when you are being challenged by the industry, when you are being challenged by an agronomist who says, "What are you talking about, mate?" You know, it's like it's some fairy tales you're giving me, and then you just pull one paper, paper 2, 3. There you go. And these things also help us in understanding how we can push this forward, how we can go beyond, you know, make good compost and make some compost extract. So all these things help us. So the reason I wanted to start with the ecological monograph made by Dr. Ingham, Dr. Trofimov, and Coleman is because this is something that is mentioned but not often read. And so I wanted to give it to you guys as the first read, because there are things that surprised me, you know, because the message that Elaine gives is simplified for the benefit of even the simplest farmer in whatever place, you know, you can imagine, but the nuance is there. And so without further ado, first thing, and I'm going to ask Adam for help here, actually, because Adam has got some really cool insights about these two fungi. First insight is that we know that the ecological monograph is an experiment between plants, bacteria, fungi, and nematodes. Now, what most people don't realize until you read it is the main fungi actually was Fusarium, and this is counterintuitive. And so what's important to note in this is that Fusarium isn't always a pathogen. And when you actually read the monograph, Fusarium was chosen specifically as a chitin decomposer, and I'll tell you why later. And they have chosen it because it didn't attack, was not a pathogen for blue grama grass, which was the plant chosen. And Mortariella was used in the part of the experiment which did not use chitin, and it's also a fantastic fungi. So, Adam, would you be able to say a few words about these two? Because I know you've got some nice ones.
Yeah, I mean, we'll definitely get into it more later, but fungi that are extremely common and very happy living in composts, right? So these are the kind of fungi we're going to encounter when we go on our mission to make really good compost. And yeah, you're not going to see so much like the basidiomycetes, the fungi that are mycorrhizal that work with the trees and stuff. But you are going to see these kind of fungi as well as penicillium and aspergillus, and so we'll get into them a bit later. But yeah, back to the monograph.
Cool. There was some other things I had in mind, but you're probably going to mention that when you get to your slide. So the other one is rhizosphere soil has more abundance of microbes than the soil free of roots. What does it mean? And what does it mean in practice for you? Because you're learning to use the microscope. You're learning to assess what's happening. So I'll give you an idea. What is first of all, what is rhizosphere soil? Rhizosphere soil is the soil directly attached to roots. So you dig out the whole plant, like you see here, and then you can wash off the soil from those roots, and that's your sample, and that's your rhizosphere soil. Non-rhizosphere soil is just the stuff without roots, right? So it's between the rows of your crop, for instance. And this is important because there was a clean seed bed, and wheat was drilled into it, and we had applied biology twice by the time, and we started looking in the bulk soil for what's happening, and we couldn't see anything, absolutely anything. And then we started digging for what's happening in the roots, and it was just a massive amount of life happening, because this is where, again, this is what Elaine has always said, that the plants push out the exudates, and so they feed bacteria, the fungi, and then everything happens around the roots. So it's worthwhile, and this is written in the monograph, it is worthwhile to look at the plant roots. If you're lacking stuff in the bulk soil, it's worthwhile looking what's happening in the roots. So that's the lesson number 2. I keep hitting the wrong button. Lesson number 3, and this is really something that I took a long while to really get inside my head. There are 2 sides to this experiment, but this one is amended with a nitrogen source, and another one is not amended with a nitrogen source, and we're going to get to that as the next lesson. But this is the unamended, where the fungi used is the Mortariella. And what's interesting here, there's these arrows that you may be able to see. You might not be able to make out the numbers, but I'll tell you. So the arrows point to the treatment in the experiment. That was the plant and the fungi. And on the right-hand side, it shows that we're looking at the biomass of the root. And the arrow that points to the number, it's 9.6 milligrams. And what that number is, it is the highest number of all of the treatments. So whether the plant was alone, the plant was with bacteria, the plant was with bacteria and with bacterial feeding nematodes, that was still lower. The biomass of the root was still lower than the plant just with the fungi. Now, what does it tell us? It tells us that when there isn't any obvious extra source of nitrogen available, if you have the fungi in the soil with the plant, you actually potentially will be getting the largest root biomass, and one of the largest above ground biomass. So fungi can actually provide the nutrition even without the nitrogen, the nutrient cyclers, even without the graziers. So that's one of the biggest lessons here, because it's easy to simplify in our heads that, okay, we've got the fungi, now we need the fungal feeding nematodes. It's absolutely, according to this, might not be necessary, right? If you have the fungi in the soil, that could be enough to get that nutrient cycling. Then we've got the fact that oftentimes is omitted, because Elaine says, make an extract, keep on applying extract, and see things grow. And things do grow. They grow because the microbes are very good at looking for stuff in the soil. They grow because there are hormones that the microbes produce. And so the actual growth rate is higher with the same amount of nutrition. But the key lesson here is that what the researchers wanted to see is what happens when you actually provide a source of nitrogen which is organic. So this is not soluble nitrogen. This is not your ammonium nitrate. This is not your urea. This is something that is natural, right? And chitin, according to this Wikipedia article, this is the second most abundant polysaccharide on the planet, just behind cellulose. And so this is a massive resource, and it's in a lot of life, basically. So they provided chitin as a source of nitrogen. And this is important, because what's important here is that we don't go into this with an assumption that we just apply the extracts and everything's going to be fine. because the microscope tells us that we've got the whole soil food web. What's important is also to measure how much nitrogen is in the soil, to then be able to see, well, what is the effect that we could be getting with that nitrogen. And so the microbes from the extract, they're actually really, really good at decomposing the organic sources of nitrogen and then delivering that to the plants. They actually are, when you actually apply these microbes, they speed things up most of the time. And then last but not least, this is on the same vein that the chitin amended and the unamended experiments, there's a massive difference in the growth of the plants. Massive difference. And this is just so important. If we just focus on, let's just put out some compost extract without understanding what nutrition is available, we might be setting ourselves for failure. And we have seen failures like that. We have seen spectacular failures like that. And fortunately, because we keep in touch with quite a few people in the community, we were forewarned. And so we were able to guide others as well to do smaller trials instead of trying to convert the whole farm, because you might be losing the whole crop if you don't do it right and if you don't do calculations right. So what this shows is, that graph is the graph of the shoot and root biomass. And you can see here that the shoot biomass at day 40, and this is important, at day 40, the shoot biomass is 100 milligrams. If I go back to this table, this experiment, the unamended experiment, ends at day 40, and the biomass, the largest biomass above ground, is 13 milligrams, right? So it's so important to understand not only the composition of the soil food web, but also start looking at the available nutrition and how can we increase that. And oh boy, we've played around with that subject as well. So that's basically it when it comes to this presentation. And I wanted to rattle through this quickly because when we look at these things, we can build on these. And I'm just going to very quickly say how much this helps us in our experiments, because we've been doing stuff in a small scale. This is a DNA test on 3 square meters. Adam has done moisture retention tests, and then since 2021 to 2025, we've been doing field trials and measuring all sorts of different things. And the whole approach of read papers to understand what could be the mechanism, and then when you do trials, try to do it in triplicates and try to do it with farmers who are interested in seeing that. And then there's one more variable actually that we have managed to crack here, and that is the variability of the compost extract. So when we started reading the papers to see, is compost extract something that's viable? And you go on Google Scholar and you click on review papers, and you go on the review papers, and the review papers tell you this experiment was great, that experiment was great, and this experiment was great. However, we cannot recommend it because all of the composts were different, and therefore we cannot compare it apples to apples. And what we have done with standardizing our compost extract into a concentrated and shippable form, that is now the first time in history where compost extract from one source can be used across an entire country, shipped across an entire country, stored in chilled conditions so that can be used outside of unfavorable weather. And now we can compare this apples to apples, where we're seeing where we can actually present this to agronomists. And this is really the battle. The battle is presenting this to agronomists, presenting this to farmers. There's all sorts of things that we've got. This is part of my presentation as well, Adam, by the way. But I'm going to now pass it on to Adam, because one of Adam's superpowers is reading reports line by line with Google, even if it takes 2,000 lines of DNA analysis, and then comes to us with some surprising stuff. And again, we can do a lot with just making compost extract. But if we are to go to that next level, where we as an industry, and I'm calling this as an industry, we compete with the large producers of chemical fertilizers, chemical inputs, we have to be able to provide evidence. And so we start with reading papers and running triplicate experiments. Right, I'm going to quiet now for a second.
Very good. I think that was a great run through of it. And yeah, my name's Adam, like I said in the beginning. Also work for Soil Ecology Lab and the gardening company that came out of it, Soil Smiths. And so my job has been to make the compost, to use the microscope, just like Elaine has taught us to do, to evaluate bacteria, fungi, protozoa, nematodes, and to get an idea of the kind of environment we're creating in the compost. And so that has been an amazing journey, and I'm very grateful for it. You know, it's like one of the best things I've done for my life. So very cool. So yeah, like we've dialed in this process where we can consistently make a compost extract. And when we're talking about compost extract, it's not in water, it's in a solid phase, right? It's in a solid phase of extract. So we've extracted it, we've made it solid. And it will go back into suspension very quickly, which is very useful for people who don't have time to make their own compost extract, and to get the rig to, extract it. And so, yeah, that has led us down the garden path of figuring out some R&D on compost. How can we make compost better? What is optimal compost and for what application? And so I'm going to talk a little bit about our R&D into the way we see compost, and that is really trying to tackle the biggest scales. So using the biggest green waste sites to tackle the biggest scales of agriculture. So when we're looking at the big scales of agriculture in our part of the world, that's mainly wheat and barley and grass, right? A large amount of our countryside is covered by grasses. And so if we can figure out how to grow them with biology that is using compost as a bioincubator, we can get very far in doing it, I believe. So we looked into a nature reserve in Israel, and we looked at the rhizosphere soil of plants. These are domesticates that are living in a feral situation in a nature reserve. And these circles you can see on the screen, Chorazim Center Area 1, those circles are different sizes, right, and different colors. And that represents bacteria and fungi, and the different sizes of the circles represent the population. So bigger circles, bigger population. So when I click on a circle, you get to see, oh, it's penicillium, right? And so this was interesting to me because we looked at 3 samples over 4 areas of the nature reserve, and we kept seeing this same kind of assembly of microbes. And this was quite important and quite interesting because penicillium, we knew from previous DNA sampling of our compost, is very happy in compost. So it's a fungi that both lives in the rhizosphere, is obviously very important to the wheat, and can cycle through decomposition, through compost, and through plant residues. Again, another area, same microbe dominating the scene, penicillium, right? When we look for other microbes that might be big circles, big populations, we also see Mortierella, the same kind of fungi that was in the ecological monograph, right? So when we're using compost as a mechanism to grow ecology and deliver it to wheat plants at scale, this is a very fitting bioreactor. And again, different area, same microbe. We didn't see mycorrhizal fungi, right? I was expecting to see endomycorrhizal fungi. We didn't find them. They weren't there in this particular situation. And again, different area, penicillium. And then, so we come back to the UK and we look into, well, we start talking to our community of farmers, and we find people that have left straw to compost spontaneously in the edges of their fields. And we look into the microbial assembly of that compost, and what do we find? The biggest circles are dominated by penicillium. So whether you're in the wild or, in a nature reserve in Israel, or you're on a farm in the UK, the assembly of microbes look kind of similar, at least to the genus level, and that is very applicable to composting and decomposition. So this is what it looked like. That's the compost sitting under a tree doing its thing, or the straw, I should say, becoming compost. And so we're looking at a carbon-rich, nitrogen-deprived environment. No one's mixed any nitrogen in there. So what would we expect to happen? We would expect it to kind of stay cold. But that's not quite what we see. So because it's carbon-rich and nitrogen-deprived, the biome modulates to fix atmospheric nitrogen to decompose it, right? And that's an important point about our kind of discovery on this, from Daniel's insight into, what might happen in carbon-rich, nitrogen-deprived substrates. So because it's so oxidized when it begins, we bale it wet, and the microbes have to make biofilms to fix nitrogen because they have to protect the enzyme that fixes nitrogen. So because they make biofilms, they get very good at building them, and this is really good stress adaptation for plants. So when we frame these DNA tests from the angle of we're looking from the biome of wheat, and we look at hormone production, and we look at stress adaptation, we see this compost made of straw is the best compost we could find for straw. It's different. It's slightly better than compost if you made it from spontaneous stuff. Like we will take softwood and coffee grounds and hay, and we'll make compost out of that. Be lovely stuff. You can grow great ecology in it, but the microbes are more generalist that are bringing the benefit and less specific. And with the wheat specific compost for wheat, we're seeing very specific microbes give the benefit. And because they have to make all that biofilm, yeah, they're good at stress adaptation. So they're good at building exopolysaccharides. They're good at protecting the plants from drought and salinity and environmental stresses like heavy metals and stuff like that. So in a very oxidative environment of large-scale agriculture with the plow and with the glyphosate, this is the best medicine, right? It's the composts made from the tissues of the previous generation of plant. And so that's how nature would do it, right? In decompositional cycles. And so the plant grows, wheat plant, it desiccates, and the microbes have to deconstruct the straw back to the ground, or it's eaten by an animal and cycles that way. But either way, it's becoming compost to get back to the ground and meet the next generation. So with new papers that happened after our investigation, maybe the same year, was it? Or the year after, this is in 2023, we see papers putting together the constellation of endophytic microbes, particularly fungi, that live in spring and winter wheat. And they find exactly the same thing as we did. You can see I've highlighted there. I won't read through it, but Cladosporium penicillium comes up again, right? So a very important microbe. A microbe able to protect its host plant from pathogens, right? From viruses, from bacteria. It's got lots of different tools to do that. And so this paper, another paper from the same year, transmission mode and assembly of seed fungal endophytes. These are microbes that live within the plant, different tissues. The endophyte communities in wheat and wheat's wild relatives. So this really nailed it home for me. It showed me that the microbes that live in the aerial parts of wheat, there's a big assembly there, and a portion of that makes it into the seed, but the rest has to cycle in the environment. And what does that mean? Well, it means composting, basically. If you take all your straw off, you compost it, you put it back on the field, or you treat the seeds of the next crop with it, you are amplifying the rate at which these cycles happen in your environment, and you're causing a feedback loop from the environment to the crop. And if you save your own seeds, you're training that crop on that environment faster. And the language is microbes and carbon, right? That's the language of these crops, these breeds and cultivars, populations, the way they communicate with the land. This is it. And we can speed it up as a farmer by making that compost, putting the extract back on the seed, and thus, closing those loops that would otherwise take many generations in an environment spontaneously. And this is us taking that knowledge and trying to do something with it. So Daniel had an idea. Let's put together wet straw. Let's stack it. Let's just start by, what is it, 2 by 2 by 3. And let's let it decompose and see if it fixes nitrogen. And it did. And if you want to, when we've got more time or in the questions, we can maybe talk about that a little bit more.
This is Dr.
But
This is Dr. Frida Mariana, our microbiologist, by the way.
yeah, 3 to 4 scale. And so, yeah. So this pile did fix nitrogen, and it's super interesting. And there's maybe a lot left on the table of this technology. But carbon-rich substrates can be used to acquire nitrogen using, and Daniel just put on the spontaneous biome within compost extract from the compost we make, and obviously from the straw in the environment. And so we don't expect this to get hot, but it does. And it gets hot for a long time. And what did it get hot up to, Daniel? 60 or 50?
This one got up to about this much, but Phil Swire, when he put his pile together, it was going above 70 at one point.
Yeah, so the influx of nitrogen is not coming from an input that we've mixed in, but it's coming from the atmosphere. And it's being requested by the microbes that can take apart the straw cellulose and feed it to the nitrogen fixers. And so that's very exciting to me. And that's showing that we're fixing atmospheric nitrogen, all this stuff wouldn't break down. And all of that is happening within these spontaneous biomes, which is super cool. And so I love cannabis. Cannabis is my plant. I know a lot of soil food webbers are cannabis enthusiasts. And so this is just to demonstrate it's not just monocots, right? It's not just wheats and barleys. It's dicots too. And they are the same kind of microbes. So in the buds of cannabis, we see penicillium. You can see cladosporium there. The same, exactly the same fungi that are existing in the straw of wheat can exist in the straw of cannabis and can be cycled in over these decompositional cycles. And so, if we just look at the roots, we might miss the fact that all these aerial parts are containing microbes, and that these microbes can be grown in compost, and compost can be used to get them back to the plant and onto the next generation. Cool. So that's me done, I believe.
Oh yeah, you just got to the point. We're talking about compost championships. I'll leave that to Nick to actually to promote that for us. But I just wanted to thank you, Adam, and I just wanted to say again, we're reading papers. Read papers. One of the things that, by the way, Łukasz Nowacki was talking about wood biomass. I apparently didn't respond to everyone, but just hosting panelists. But champagne piles were one of the clues for me that this could be happening. And then young Red Angus was showing off his Johnson soup piles, and then, oh, this is just a maize straw pile, and it's. And it's gotten hot, and I've got compost out of it. And then I found a paper where there was an experiment. It was a 4-page paper. It was an experiment where they paired a fungi and a bacterium, a nitrogen-fixing bacterium together, and they got them to cooperate. And then Frida found a paper where they did an experiment in 1986, literally a year after the Ecological Monograph, which said that you can not only use to decompose straw and get some nitrogen out of that, but the actual rate is so high that we could be getting 300 kilograms of nitrogen per hectare. So the thing is that, again, my message here is let's read papers, and let's start with the Ecological Monograph, because the most important lesson in the Ecological Monograph is the microbes that we produce in compost, they're trained to decompose stuff. So when they find a resource which is locked up nitrogen within bigger molecules, they'll jump on it and they'll decompose it and they'll send it to us. And then let's just keep on experimenting, because what Adam just presented, this was me trying to answer the question of how do we produce nitrogen on farm. We know now that the free nitrogen fixation is only 20 kilograms a hectare. If we want something more, then it's usually legumes. What else can we do? And then realistically, we need to feed sugar, a lot of sugar, to nitrogen fixers to be able to do it. And where does the sugar come from? It comes from the straw. And so we had to figure out a way to do that. And so it's a very exciting development that really starts off with these basic understandings. So let's read more papers and let's experiment more. And let's make more compost.
Well, yes, and that leads nicely on to your first compost championship. I hope there's some rules in this, Daniel, because I can see a few people potentially cheating here. So I look forward
Don't
to
worry, we're not entering ourselves.
ah, right, right. I need to buy some gloop, all right? Can you send me some?
That's a good one. Nice shortcut. So this is a few years back, farmers were sending us samples and we did this fun leaderboard and people got excited and started, saying it's like, oh, do I have good compost? Can I be put on the leaderboard? And they wanted names on it. Like literally, I first did it anonymously. You can still see it under the soil testing tab, but people wanted to put their names. They were competitive. And now, after so many years of us doing this, because we've been doing this full time since 2019. After so many years of doing this, we are surrounded largely thanks to the Soul Food Web School. By the way, this is the benefit of the Soul Food Web School. Everybody is that the community has grown, and that means that the talent has grown, and that means that the all sorts of small and large makers of compost and farmers making compost, they're everywhere. And so we're surrounded by this wonderful community of people just making compost. And they understand that they are basically at the tip of the spear that's leading the charge, and the sort of fortress that's just sitting on the sidelines really doing not much is the green waste industry, the people who I wrote that article for. And the green waste industry is kind of, they're making money on the waste coming in like a landfill, and they have very little incentive to actually produce good product. Unfortunately, it's not their fault, it's just how it's been designed. And now we've got all this massive group of people who understand compost, who want to make great compost, understand biology. And so we thought this would be really the best way to showcase what's out there. And what we offer here is that, first of all, this is, unfortunately, it's unsponsored. So what you're doing is you're testing your compost. This is the price of entry. You're testing your compost with us, but you get that test, so you start learning of it. And to make it more valuable, what we say is that anybody who participates will join a weekly call where we'll be sharing our knowledge for free. We'll be answering all questions. And we've had compost which was 16-1 fungal to bacterial ratio. We had other people who did 20-1 fungal to bacterial ratio. If you're interested, we've done all these things. And also, if anybody wants to spend days with us learning, there's going to be a 20% discount for anybody who wants to sign up for our training, who already participates in the championship. And this is going to be fun, and this is going to really show up in all the news that are positive. And so anybody who's in the UK, just show us what you've got, because I know somebody's got wonderful compost there. And so, yeah, Nick, this is going straight into you. You've got literally, Adam's got one bet in his mind, so I'm going to bet on you, and then we're going to drink to it.
I was
So,
going to ask that. I was going to say, Nick, are you running for that? Because I
Well,
vote for you.
well, that's incredibly sweet,
I
Daniel and Isadora, and I think Adam's won with his horse. But I don't think this should be open to Soil Food Web mentors, Daniel. That's great. And I think you've got
you're just scared. That's all, Nick. I'm sorry. Just
well, what it has done certainly for me is we've seen many people coming to us, and I'm sure Isadora, and I'm sure you guys get it all the time. People coming up and saying, "Look, I've made great compost," and you kind of say, "Okay, right," and you want to stick it under the microscope as quick as possible, just to reinforce to them that yes, it is great compost, or actually there's a bit more work to be done. And then as Elaine always says, get that microscope out and get it working, and you'll understand exactly what you've got in terms of microbes.
that's
So
that's very true. That's very true. The microscope has been an essential tool for making great compost and the goop. And so, if this is something that is absolutely indispensable to get that going. I will say that this is the biological part, and if we want to have a broader view, don't limit yourself to the microscope. Look at the nutrition. Even look at the DNA, like Adam was showing. This was the conversation I had with Elaine when she turned 70, actually, 3 years back, and I said to Elaine, you said not to bother with DNA, with species level stuff, leave it to your grandchildren. And I said, do you know, I could be your grandchild, couldn't I? And she laughed and he said, fair point. You go ahead.
Brilliant.
I
Guys,
get that.
yeah, sorry. So look, guys, thank you very much indeed. We're on we're on course now to get where we need to get to for our hours worth of Q&A, and I think we've got quite a few questions, Adam and Daniel. So you better get yourself ready and take a bit of a breather. So can you flick on one more, please? Is because look, guys, we've got this great opportunity here now. The school, the Soil Foodware School, is now being run as a public charity, which is a gift from Dr. Elaine to the world, right? After 45 years of complete dedication to a mission, the next generation of Soil Food Web practitioners are carrying the torch forward for her. And I think, as Daniel has said, and Adam, and certainly me and Isadora, we wouldn't be where we are now if it wasn't for the amazing work of Dr. Elaine. So all we do is thank her. And we're reaching out to the community to support our mission going forwards, because we need to keep this going, right, guys? And we need to keep and increase the accessibility of all the educational programs and amplify it around the globe. This is so important. And in celebration, Dr. Elaine, we're offering her amazing flagship foundation courses with the largest discount we've ever granted. And this is live now, guys, and it's on the screen. So we've gone down from $5,000 to $1,799, and that's up until the 6th of November. It's just an incredible discount. But on top of that, we've added some other little bonus sessions to our new cohort experience. During our program with all the students, you'll be learning alongside your peers through weekly live study sessions, guided by expert mentors who typically teach at workshops. So unfortunately, you might get me, or you might even get Isadora. How about that?
Yep.
So look, please join this amazing Soil Food Web community that Dr. Elaine has been working on for 45 years, and be part of this global movement, which is just an incredible community. And also, if you've enjoyed today's amazing presentation from Daniel and Adam, and I spoke to Daniel earlier this morning, and I was concerned that he wasn't going to finish on time, and he assured me he would be, and absolutely he's true to his word. So Daniel, Adam, thank you so much for that amazing insight. Absolutely incredible. You've really started off this series of webinars well for us. Please, if you've liked today's webinar, follow, subscribe, do all the usual things. And that'll be absolutely great. But look, guys, we're also incredibly lucky because we have a special guest with us. If you can flick forward one more, please, Isadora. We are so lucky to have with us Dr. Russel Ingham, co-author of the Ecological monograph. And is he there with us now? Can anyone, is he going to join us? I can't see anyone on my.
Yes.
Ah, yes. Dr. Russell, how are you?
Excellent.
Thank you so much for joining us. We really appreciate it. Thank you. So I have a question for you, if I may. How does it feel to know that 4 decades later, your research on nematodes and soil food web has influenced how many millions of people around the world to understand soil and an approach on agriculture? How does it feel?
It feels really good. I can't take too much credit for it.
Well, I think what you've done is just utterly amazing, and we all thank you for your dedication and devotion to this incredible topic and the work that you've put forward. Just utterly amazing. Do you have anything else you'd like to comment about from these 4 decades of works on nematodes?
For decades, a lot of people working on this stuff other than me.
A lot more people were involved, were they?
Yes, there were.
Well, we absolutely thank you for everything that you've done for this community and for the Soil Food Web. It's just absolutely fantastic, and we feel incredibly honoured that you're joining us today on this first webinar to celebrate Dr. Elaine and the work that you've both put together for the Soil Food Web.
Well, I appreciate that, of course, but like I said before, there's a lot of people around me, other than me, who worked on this. I sort of set the foundation, as you said, but if it hadn't been for all those other people following through on that, it wouldn't have gone anywhere. And been off the afterthought. But it's bibliography.
Well, thank you so much. That's really great. Daniel, do you have
Always humble. Always
Yeah,
humble. Thank you very
absolutely.
much. Thank you very much. And yes, I can see Jenna in the background. Thank you very much for joining us as well. I'm going to say it. This is Jenna Ingham. This is the daughter of Elaine and Russell, and she's absolutely wonderful, but she doesn't like the microscope. I'm sorry. She did not pick up after the parents.
Look,
So
this is
that's
what 40 years. This is what 40 years of research does. Your daughter doesn't want to have to spend her summers.
Jenna, that's a normal thing. Every parent and child, we have this relationship. If my dad does this, I'm not going to do it. Don't worry.
Yeah, I was counting protozoa in a microscope when I was like 7, so I think I'm good.
Good
I
job.
think that was the first thing when I was introduced to you, Jenna. That was the first thing you actually announced, that I just
Yeah.
don't do microscopes, right? I just
Everyone has always asked me what I think about all this, and I was like, look, this is like life for me. It's very normal. I had soil in my fridge since, right? I literally took naps in the lab underneath tubing, right, and microscope desks and funnels for days. So it's basically in my blood, so to speak. Sometimes I lean in, sometimes I lean out, but it's great to see everyone. Thank you for having my dad. It's really cool for this, so very excited. Thanks for
Thank you
having
for
us.
taking the time. Thank you for everything that you've done.
absolutely. And Jenna, Dr. Russell, thank you very much indeed for taking the time and joining us this evening. And love to Dr. Elaine, please. And thank you very much indeed for joining.
Let's keep it all going, guys.
Take care. Thank you very much indeed. Okay, guys, have you had a chance to have a bit of a breather? Yeah?
Everyone
Okay.
is excited.
Fantastic. So the first question, Isadora, is
Yeah, Joanna has asked.
what is
Sorry.
what is the ecological monograph? So what is it,
is it?
guys?
Hopefully
It's a
Daniel
paper.
can explain that.
It's a paper. It's basically a this was actually that particular paper was it's not the ecological monograph, it's an ecological monograph. It's actually was published in
1985,
in a publication that was a compilation of ecological monographs, and so that was one of them, and it was like pages 109 to 140 or something like that. So it's a big publication, but
like
it's a big
Nature or
thing.
something like that.
What's that?
Like Nature or something like that, isn't it?
Exactly, and so it is a paper that that answered quite a big question, because when you actually read through it, they were the researchers. This is Dr. Ingham, Dr. Coleman, Trofimov. They were first doing a literature review, and they were saying, okay, well, we know that these protozoa, these nematodes, they do something, and they might be actually contributing to the fact that plants grow, but nobody's ever actually proven it. Nobody's ever actually exactly said this is the effect on plants. And so that's why it's so important, because it actually demonstrates that these graziers of bacteria and fungi, they actually increase the abundance of nutrition in that rhizosphere. And so that's what that paper is.
If you scroll back in the chat, I put the link to the actual section of the specific monograph.
Fantastic, guys. Thank you very much indeed. Appreciate that.
We have another question. Should I read that one, Nick?
Go for it.
Well, when talking to farmers and agronomists who do see the damage of chemicals and the value of soil life, I am always met with skepticism for microscopy assessments as compared to DNA analysis. But that has been hard to defend with scientific literature. Can you comment on this? What is the
Yes.
selling point? Go ahead, Dan.
Yes, it does two different tests. DNA analysis is a qualitative analysis, not a quantitative analysis. It gives us an insight into potential functions, especially if you do it with a service like biomakers who focus on that for farmers. The microscopy is a quantitative, but also there's one quality, there's one particular thing that also often escapes students, is that it's what's anaerobic and aerobic. That's the qualitative analysis. But the quantitative analysis gives us an insight into how much of that nutrient cycling you're going to get, how much nutrition release you're going to get. There was a really cool test that recently we did for a client, and Adam just basically pointed out, look, if you look at the microscopy, and then you look at the Solvita burst, and then you look at the available nitrogen from the Haney test, they all line up. And so suddenly your bacterial count can be a predictor of your nitrogen release from the soil. And so those are completely different tests. And so we need to look at them from this. Traditionally, we have used microscopy for developing great compost because that is really necessary. Less so for seeing progress in the soil, but these little nuances, they can provide value to farmers on the soil.
Yeah, I can add to that as well. Like when we look at these samples of DNA in the rhizosphere of wheat, we're looking at the kind of total pool of microbes that are there. We're looking at all the DNA. So we're looking at the spores. We're not necessarily looking at active things. And when you look down a microscope and you see a living fungal hyphae, you're looking at active fungi. So you put them together, you can look at the assemblage, the latent microbes that the plant has access to kind of manipulate for different things. But yeah, it's not until you really use the microscope you see what's active right now, and it might have some blind spots. For the best part, it's like a very cheap way of developing really good compost and making sure that compost has a developed ecology. And you don't necessarily get that with the DNA.
And that last point on anaerobic versus aerobic, or wet versus not terribly wet. We usually sort of finish the training in the school, and the one thing that stays in most people's minds, oh, there's a ciliate, therefore we can potentially be going into wet conditions. But I'm going to tell you now that all of the groups actually show that, the morphology. So why does Elaine use the word oomycetes for the opposite of the beneficial fungi? When there can be a conversation, well, what does it mean? Oomycetes are water molds. There are water molds. When it's getting wet, you're starting seeing oomycetes. And then when you're looking at protozoa, you're looking at you can see that on the sort of chart of your morphology, your flagellates and your testate amoebae, they're going to be in the sort of more aerobic, drier conditions, and the naked amoebae and the ciliate are going to be in the wet conditions. That's your protozoa. So you've got your fungi, your protozoa. Then you're looking at your bacteria. When you're starting to see, the spirochetes, the vibrios, that's your wet conditions because it's going anaerobic. And then the typical rods and cocci, that's your aerobic conditions, right? This is a simplification, but then we go down to nematodes. And even if you take water that's pulling in on a compaction layer, and you see root feeding nematodes in it, so even root feeding nematodes could have a start in wet conditions. And so what actually that method shows is a demonstration of what conditions are actually in the soil, especially in those compaction layers, right?
Yeah, you're like learning crime scene investigation forensics for soil, and that is giving you an idea of the redox environment that is there. Otherwise, it wouldn't support aerobic life.
That's right. Yeah, I love to compare different kinds of tests. I've also used DNA and microscopy, chromatography, Solvita, anything together. It just gives me more confidence, in fact, that the things that we are doing, it makes a lot of sense, and this could be it's a very valid way to go. Is there any particular moment that that you would recommend a farmer to use DNA versus microscopy, that you think it'd be more valuable to use both of them or one of them compared to the other?
I guess making compost, making your inoculants. The microscope is so useful because you can just go to the compost pile, throw a sample under the microscope and view it like within an hour, get an idea. You can follow the succession of microbes in that pile, and it costs you very little. Whereas even at the best, most affordable DNA analysis is 235 quid a sample. So every sample I'm throwing money at a situation. So it's good for the biggest scales, or people like us that want to dig into the fine nuances of what is the most optimal compost. But for you on your farm, I think the microscope is way more accessible to begin with, and it's a great gateway into learning more. Anyway, so yeah, I think
And
that's it. It's the accessibility.
and guys, just to drop in rotations and crops rather than we're just using wheat, so it could be beans or peas within a farming large scale rotation. What impact does that have?
Uh, usually rotations are there's two main reasons for rotations in agriculture. I mean, Adam's gonna, and Unique probably can say more about this. By the way, one thing I didn't say during my introduction, that I'm not a farmer. I don't come from a farming background. I'm actually a recovering townie. Okay, so I try to learn from people as much as say things out of my mouth. But when it comes to rotations, there are two main things that would warrant rotations, and one is pathogen accumulation, and the other one is nitrogen depletion. And so those are the two main reasons why you would be looking at rotations. And that pathogen accumulation is an interesting one, because what my question is, for development, for all of you as soil food professionals, is what can you do to actually limit the pathogen accumulation when you have access to good compost? I actually don't have or we don't have as a lab, don't have enough experience when it comes to that. But the anecdotal evidence we've seen is that the application of biology in winter months, autumn and winter months, actually have got a positive effect on reducing the pathogen loads in the soil in the growing season. So could that be something that helps actually reduce rotation if that's the aim of the farmer?
Yeah, there was a great study with this little natural farming operation called Shumay Natural Agriculture in the UK. And they plant into the same beds, they grow the same crops in the same beds, and they save seed, right? And so in this study, they had the highest Brix in their tomatoes, and those tomatoes are going into the same, the residues of the previous year. There's no rotation, and they're achieving the highest Brix in this study. So what I presented suggests that maybe these organisms are prepared in nature, at least. And obviously, it's slightly different to agroecologies, maybe, but these organisms are preparing the soil for the next generation. They're investing resources, and the biome is working to prepare for the next generation. So, rotation kind of works against that. But then in agroecology, because you grow monocultures, it's a nuanced thing.
Adam,
So,
have you, sorry, one last thing, Nick, and we'll switch to the next question. Have you played around with Jadam?
Yeah. I came at all this through natural farming, and
well,
trying to understand how that fits.
Jadam is actually comes from the sun, right? From Master Cho. His name is the sun.
Cho,
So again, those family conversations, dinners must be very awkward, and he's just trying to do things a little bit different. But I really like this idea, and it's very similar to what you're saying, that they're talking about specialization, right? They monocropping, they're not intercropping, they're planting in distances, and they're not rotating their crop. And it's really interesting. It is a methodology, but there must be some kind of greatness to that madness too.
Where my mind goes is this. We have these people holding these heritage varieties that are adapted to bioregions, right? An example in the UK is beer, which is a type of barley the Scottish people grow in the Highlands and in the islands. So it's salinity adapted, right? We could take the straw of this Scottish barley and we can make compost out of it, and we can treat the high yielding varieties that we use in conventional agriculture. We can almost make a biome transplant to the high yielding varieties to give them more resilience in the environment, like the highlands and the islands. And the more heritage varieties that maybe the conventional guys don't use because they don't yield enough, they still worth lots because they contain a lot more diversity within the pool of microbes that exists in their biome. So I think there is definitely something to that for sure. Yeah. And sorry, Nick.
Go for it, Adam. Sorry, let you finish off.
No, ask your question because I was going to go to the second part of this question that someone's put in. There was like a second part to it, like what the farmers usually come back to them and say, and I just wanted to dig into that a bit. But what were you going to say, Nick?
All I was just going to, are we going to get to a point at the end of my career where my career has been revolved around rotation being absolutely important to a farm? So are we going to get to a point where we actually solve the soil biology and get it where it needs to be or where it should be for years and years of degradation using synthetic inputs? Are we going to get to the point where we could grow wheat after wheat after wheat after wheat and go to a not monoculture, but a main single species rather than having to do a typical farm rotation?
Yeah, I think there are these dual purpose microbes that are both decomposers and symbiotrophic. So they work in symbiosis. And then there's dual purpose microbes that are decomposers and they're pathogens as well at some points in life. I think the longer, the healthier your soil, the faster the residues disappear, the less likely there is to build a pathogen load, and the more likely you support symbiotropic decomposers that cycle in the environment. So I think maybe, we can get there. And I think the next bit I was going to say is there was the comment that came back. Oh yes, it's there, but it doesn't mean anything. Talking about the fungal biomass and bacterial biomass that we see on the microscope, right? That is the fundamental nutrient source in nature, right? The nitrogen isn't coming from bagged nitrogen. So this is what the farmers need to understand that you're trying to get through to, right? The bacterial biomass and the fungal biomass is the preferred nitrogen source. And so if we quantify bacteria and fungi as bagged nitrogen, we're showing them they're saving money because the plants are accessing nitrogen from chitin, from fungal biomass, from insect biomass, from mesofauna biomass like springtails and mites, and from amino sugars in bacteria and in the soil. That's it, you know. That is the challenge. We have to get those resources out there and get them sticking to the soil as amino sugars and as chitin. That's the message of the ecological monograph.
We've experimented so much when it comes to finding these alternatives, the actual like for like, like this, the farmer wants 200 kilograms of nitrogen per hectare bagged, like this is what the farmer wants, right? 250 preferably, okay? But now in the UK they use 200 kilograms, that's normal. In Denmark, actually, IB tells me that they use 140 and that's a cap. But let's start with 200 kilograms, right? Okay. Now the question is, where do we get 200 kilograms? Because that's what the farmer wants. And so, if we are used to having 10 tons of wheat per hectare, and we want to do it year in, year out, we need to have healthy soil and we need to have enough nitrogen to be able to do it year in, year out. And this is the sort of questions that we've been trying to answer. And one way that we see it is through that straw compost. Another one is we were trying to remove the negative effects, the oxidizing effects of synthetic fertilizers. And I had this crazy idea. Well, what if we gave microbes nitrogen and carbon in the right proportions, and then we lock up the nitrogen? It could be urea into microbial biomass. Then I made a search, and there's a company called Terraganics, and they're doing something similar already. Okay, so this is not completely stupid. And Adam, took upon himself to develop that, and we ended up with a product for retail because we couldn't find a cheap carbon source basically for farmers for large scale. But the point I'm trying to make is, what Adam said. We need a resource, just like the ecological monograph says. The ecological monograph used chitin as a resource for that nitrogen. And that is a reduced form of nitrogen, which is safe for everybody. It's safe for the plant, it's safe for the microbes, it's safe for the soil. And we have to have all of these things in mind. We have to have in mind the physical, the chemical, and the biological properties of the soil. They have to be in tune.
Yeah.
And so when we achieve that tune of soil in all these three aspects, this is when we have a chance of having same crop, year in, year out. And the thing that limits us is the number of disturbances that we use. And I use the word disturbance for anything that is physical or chemical. Usually farmers don't use biological disturbances, but anything like a plow or anything like that is a physical disturbance. And then you've got every possible chemical used that's a chemical disturbance. And we've actually have shown it in tests to be true, not only read papers. And I'll give you one anecdotal example about that. There was a guy called Masanobu Fukuoka. He was Japanese. And Masanobu Fukuoka has 1/8 of an acre of rice paddy. And he did nothing to that rice paddy. He just returned the straw, which is a very interesting thing, right? He just returned the straw to that rice paddy, not in neat rows. He just spread it by hand. He only kept that paddy wet for a week because he understood that rice can withstand water, but weeds cannot. Therefore, all you need to do is wet the field for a week, kill all the weeds, and then drain it, because now you've got an aerobic structure to the soil, which is healthier So again, it's healthy, and then you're putting in the straw back, so you're giving the ability for the microbes to fix that nitrogen again, and the whole cycle continues like that. So that's one anecdotal thing that he was doing for decades, basically, and things like that inspire us to experiment with these things. So my current view, my current vision for something like that is the current system is kill everything with glyphosate, prepare the seed bed, drill the seed with fungicide coating, then kill everything with glyphosate again, and then start with insecticides and fungicides throughout the growing season. In the meantime, you're going to be adding your fertilizer, right? So that's your typical conventional system for wheat. And what we're saying is, could we replace the glyphosate with a shallow plow and a mowing of a cover crop? Because that's what our friend Dermot does as an organic farmer in Scotland quite successfully. Okay, well then we get rid of the glyphosate. We've already demonstrated on at Gallia's. I'm going to actually go back to that slide. Bear with me. I'm going to use my buttons, and I can do that because I've got buttons here. So I'm getting close to
taken Isadora. We should have taken the use of those buttons off him.
I've got buttons.
Yeah,
you can't
I know.
stop me now.
I know. We will have to.
You can't stop me because I'm getting there. I'm getting there. This is very important to me because I'm talking about removing those disturbances, right? And so there was one test done by a farmer this year on spring barley. And Ed came to us in February to learn to use the microscope, and then he bought some goop. And I asked him, are you going to use pre-emergence herbicides? Now, for anybody who is not a conventional farmer on large scale, pre-emergence herbicides means this. You have just drilled your seeds into the soil, and now 2 days later, or within sort of a week, you come in with a herbicide application before your plants start growing, before they come emerging from the ground, right? And you do that just to make sure that there is definitely no weeds, and it pretty much sterilizes the soil. Glyphosate is an antimicrobial. It was registered as an antimicrobial, and so it affects both plants and microbes. So it kills all of those functions. It's a disturbance. And what Ed found, because I said to him, can you not use the preamps? And he says, first of all, my agronomist is going to cry. And then we agreed that he's going to do a split trial. And here you can see that those highlighted results come from two separate fields, where adding the biology to the seeds, but not having that pre-emergence glyphosate, gave him an extra 0.5 ton per hectare of yield for this much goop, 400 milliliters per hectare, right? And so, and you see that where the pre-emergence was added, the gain was half. So we can see that there's a direct effect, that using that disturbance, kills the microbes. So can we use a shallow plow and a flail or a mower before we drill? Then we drill and we coat the seeds with biology, right? We add a little bit of nutrition to that to get a good start for the plants, from the start. And then we don't do the pre-emergence application. And then we apply something like straw compost, or something like composted manure, or something that is an organic source of nitrogen, right? And we make sure that biology is there for the nutrients to happen, right? Nutrient cycling to happen. And then we tweak the nutrition of the plants so that they are healthy. We're not treating the field as a hospital bed. We're not feeding the nitrogen intravenously and then giving it drugs so that it doesn't get sick. We want a school where the plants are school children, and they're getting healthy lunches, right? So we're just tweaking the nutrition. We're doing SAP analysis to tweak the nutrition, make sure that they're healthy. So they're getting the nitrogen source from that chitin, from the biological mass. They're getting bits of nutrition which still didn't get to the plant because maybe the system is not working perfectly. And then, if really it's necessary, then we'll come in as a nurse and we'll clean the wound because there is an infection, right? Only then. So that's the kind of system that we envisage that limits those disturbances, and that can create a healthy soil that potentially will give you that ability to build that biology that works with that particular crop year in, year out.
Well,
Brilliant.
all I have to say is
Brilliant.
that thank you, Anonymous, for this really long and nice question. Thank you, Daniel. Thank you, Adam. This was, I know
Isadora, take that button off him, please. Whatever
No.
you just
we can go on
take
and
the
on.
take the button off him.
Yeah, I know we can go on and on, but it would be nice to. Oh
Yeah.
my God, it's Anonymous with another question, or no?
No,
Is
no.
that's the same
Next one.
Sorry.
Next
Okay.
one.
So the
That's
next
the one.
one.
Yeah.
Will saprophytic fungi break down the chitin produced by AMF fungi when the plants are dead?
Yes. Yeah.
Next question.
Trichoderma chitin-elicit fungi. Fungi that have, enzymes that break down chitin are going to cycle that, yeah.
Fusarium, Trichoderma, there's many others.
Yep. Awesome. Thank you.
Okay.
So
Yes.
go ahead.
Yeah, so if straw compost produces nitrogen, would the same be true for compost using fallen leaves?
Yes, I would say yes. Obviously, if we want to be scientists, we would be measuring everything, right? So I'll tell you this. We measured straw. So we sent it to NRM, which is a lab here in the UK, and we got the total carbon, total nitrogen, the dry matter percentage, and we got the carbon to nitrogen ratio. And so the starting straw was 87:1 carbon to nitrogen ratio, right? And the total nitrogen was 0.5%. And so we plugged in everything, and we got doubling of that starting nitrogen when it comes to the total amount. Like if we were to measure it in kilograms, we got an actual doubling of the nitrogen. Now leaves, they're probably even wider carbon to nitrogen ratio when it's starting, and so for leaves to be decomposed, again, that's a very good source of glucose. But that's not enough for bacteria and for fungi to be able to grow. They require to build amino acids, and amino acids, they contain nitrogen, and so this forces the ecology to select the microbes that do it. And this is actually a very useful way of thinking about this, because what we have seen, and Adam actually has been really instrumental in this, because again, he's a geek reading through DNA analysis line by line, species by species. What we found was the community selects who actually appears to do what jobs based on the environment provided. And another example of that is one of the first examples was there was a pile of compost built by a friendly hippie, Tom, who used to work with us as well, and he just basically put a plastic hose through that pile to heat his water shower, and to heat his shower water, and Adam found in that huge list of microbes with the potential of decomposing plastic. And that was like the first thing. It's like, oh, it just spontaneously appeared. And then when we did DNA analysis on the straw compost, again, 2,000 species, when we looked for nitrogen fixers, these were specifically cellulose decomposing nitrogen fixing bacteria. So these guys basically were there because they were able to cut down cellulose into glucose, and then use the glucose to fuel the nitrogen fixation. So yes, I would say this can happen as well, because this is also a pile that does not provide nitrogen from the start, and the microbes are forced to do that.
Okay, so I've got a question which is really burning in my mind from many years of large scale agriculture. So if we're looking at this straw from barley, wheat crops, it has been all combine manufacturers' tasks to spread straw evenly across the field. And if we don't, and we see slightly thicker rows of straw within that field, it robs nitrogen potentially, maybe, and we see crops struggle where more straw has been added to the soils. Is that right? Is that how we should be thinking about this, Adam?
Can I take it? Yeah.
Please.
Raring to go. Like,
You
yeah. So
were.
the thing
I
is
fired you up there, Adam. Fired you up.
the key thing with this technology, and it really is a technology, right? Is is the oxidative stress. So if you take all these leaves and you put it in a airy condition in a cage, there's too much oxidative stress for nitrogenase to work, the enzyme that fixes nitrogen. So it's a bit different to when we're making the optimal biocomplete compost, where we're putting in all the ingredients to create this lovely ecology that has everything, right? It's more stressful and it requires more specialization, right? So we need to protect nitrogenase from oxygen. So by baling it wet and packing it all down so oxygen can't get in very well, we support nitrogenase function. And where that can happen, we can fix the nitrogen to decompose the straw. When we spread it on the field, there's so much oxidative stress from sun and wind and rain, it induces effect that stresses biofilms. And so microbes might have to rob nitrogen from other places to decompose it. But it will still be happening in some reduced capacity. But when we put it all together and we create this Goldilocks environment for this well-studied enzyme that is crucial for life on Earth, we create this Goldilocks environment for this process to happen and we acquire nitrogen. Now, our acquisition is 10 kilograms of nitrogen per ton of straw per hectare, right? So if you
Per ton of straw.
sorry, per ton of straw. And then per hectare, we might get 4 tons of straw. So we get 40 kilograms of nitrogen. In the lab experiment Daniel briefly talked about, they got maybe like 200 or just over 200 kilograms, I think, was it? So
300.
three. So there's a huge potential left on the table there for optimizing this, kind of spontaneous process that we've documented. But that's it, oxidative stress. Same reason I'll die and you'll die is, what will stop this from happening? So we got to look after and nurture these piles and think about these processes. And we do that by reading papers and getting used to these concepts.
Well, let's just hope we don't die before the end of this webinar. Let's get to the next question because I think there's loads of them piling up.
Yes, thank you, Adam. Yes, if we are trying to improve grass growth, should we be using grass, hay, or silage in our compost rather than just using wood chips and livestock? Straw, bedding manure. Whoa, okay, hold on a second. There's no punctuations in this sentence. It's hard for me. Bedding manure in our large-scale windrows to get more grass-specific fungi. I don't know if anyone understood. So we're trying to improve grass growth. Should we be using grass, hay, or silage in our compost rather than just using wood chips? And livestock, straw bedding manure in our large-scale windrows to get more grass-specific fungi? Stephen, please.
Adam, did you want to chime in on this one as well?
Yeah, we do. We're doing it for that reason too. And yes, we include hay, or we might include spoiled silage. Silage is a technology again of compacting and anaerobia. And in anaerobic conditions, there might be a different selection of microbes there for a short time, but they're both viable sources of biology and of nitrogen for composting. So we use hay and we wet that hay out for a decent amount of time so it gets nice and wet before we start the composting process. And
Has
we
that
will
hay?
use hay in the same way we're using straw, like to make the straw compost, because it's already got the nitrogen, so you're not going to fix the nitrogen. And if you pile the hay up too high, it might catch fire. So we use it critically when we're doing the straw compost, we're using straw, not hay. But when we're making our lovely biocomplete, ecologically developed compost, we're putting hay in there for sure.
I've got
You're
more to add
wetting.
to this. Sorry, Nick. I've got a bit more to add to this question myself. So, it's good to think of broader ecology. Stephen is actually on the right path there, I think, in my opinion. So the way I see this is this. First of all, think about why you're doing this. You're doing this because you're going to be feeding animals, most likely some cows, And these ruminants, they evolved with grasses, right? 65 million years of evolution, grasses and ruminants. So, so that's one thing to think about. Okay, does manure fit into this? Yes, it does. Okay. Second thing, does grass fit into this? Obviously it does. Hay, silage, all of these things fit into this. Then there's the case of wood chip. Why are we thinking of wood chip in the first place? We talk about increasing the fungal component. Now, if we actually really want to push that fungal component, what are fungi good at? And this is what Elaine talks about in her training as well, right? What are fungi good at that bacteria are not so good at? The more complex molecule, the less likely it is that a bacterium can actually cut through that molecule, right? Fungi are better at more complex molecules. If you think about wood, this is something that Adam educated me in. Wood is Earth's first plastic, and this is from what I understand, this is where coal comes from, where wood was not decomposed for the longest time, and it just basically sat in bogs, and that's where coal comes from. But then fungi came about, and they figured out how to decompose wood. And so, if we want more fungi in that soil, then the simplest thing to do is to start adding more wood chip or composting with wood chip, because that's lignin. Straw is 60% cellulose and hemicellulose. Before fungi can jump on that, it's going to have lots of competition from the bacteria. Lots of competition. We think about this as a brown input to compost, but it is a bacterial food when you think about this. But wood isn't. Wood is a fungal food. There's actually a very good paper from years ago that looked at, what woods, what other things, to use to actually increase that fungal component in soil. And then there's one last thing I want to say. Let's say, our aim is to increase fungi. Great, that's our aim. Does nature care about that? No. It basically, what we have seen, for instance, in small potted experiments, is that we can put the same soil food web composition, the same extract in a grass, in a hemp plant, or a fruit tree, or a pine tree. And the thing is that it was the same thing. But then after 2 weeks, when you start looking at this under the microscope, the hemp or the grass is mostly bacterial, and the pine tree has skyrocketed in fungi because that's what the plants decided to feed.
I have a really quick follow-up question, because I live in a very, very arid situation. And we keep talking about we need to put more carbon back in soil, and one of them
Yep.
is just leaving the straw and everything. But one of the situations that we have here is that the straw just pretty much oxidizes and fossilizes in the surface,
Yep.
and it doesn't get decomposed. I don't know if you guys have experienced this.
And can I add to that before you go for it, Adam? Because I know you're going to. I would agree with that, and also say in some particular fields where the clay content is quite high, and farmers doing a lot of cultivations, and there's not a lot of oxygen in the soil, and you get some of those on those lovely Hampshire soils. We see sort of 2 or 3 years later, we can plough, cultivate a field and still see the straw only slowly starting to decay.
Yeah, so back to the Goldilocks zone, isn't it? It's like if it gets too anaerobic, it will be too fermentative and it will just pickle. So the aerobic organisms have to have access to oxygen to get at the cellulose, but the nitrogen fixers to acquire the nitrogen to fix it, that needs to come from the biofilms in a more fermentative
Okay.
environment. So yeah, it's this Goldilocks zone. It can't be too oxidative. And in a situation like a semi-arid or arid environment where it will just dry out and not do anything because of the lack of rainfall, we need to bale it, compact it, and wet it out and keep it wet or in a shaded condition, not just again in the middle of a field, but shaded from the wind, shaded a bit from the sun. And you have, yeah, there'll be more of a conducive environment with the decomposition. And then we're making this really specific compost that's very specific to wheat, and we're cycling microbes from the environment. And with all that lovely humified substances that will occur in there, we're adding stress adaptation back to the oxidized condition of the soil. So we're protecting the plants during times of drought from salinity, from heavy metals that might be more available because of lack of organic matter. And so, yeah, this really, this straw composting technology really need to understand the biological processes that underpin it. And they are a little bit different to, what the thermophilic composting we learn with the Soil Food Web. But it's just an expansion of your understanding into these different enzymes and how these microbes work, and not being too oxidized while also not being too waterlogged. It's
So
this balance.
to speed up the process, would a nice, once you've got your piles of straw baled tight, and in ricks, would you then help the process by adding, a nice protozoa cocktail or an extract, and drench it rather than just wetting it?
Yeah, as long as it's not got nitrogen in it, you don't want to add nitrogen, you want so, but that's exactly what Daniel did. Just a coarse compost extract was poured in. I think you can elaborate on that.
Yeah, it was just literally just a bit of leftover extract in a bucket. I just poured it onto the 6 bales,
Yeah,
and then I think I added some worms later, but I can't remember if I even added the worms.
cool.
To just wrap up on what Isa was saying, yeah, if you're basically faced with, and this is something that I'm being told by a friendly agronomist, called I think Tim Ashley. He was telling me that, or Mark Palmer, was it Mark Palmer? You go to the east side of the country and straw just lays there, like you said, Nick, right? Just lays there and does nothing. So if you know that these conditions prevail, you're limited to what that layer, which is completely protected by otherwise dry organic matter, and how deep can you make that dry litter, basically, to have a layer, between that dry matter and your soil, which is protected and has the ability of capturing moisture, so that those biofilms, as Adam was saying, can be created. So that's your limitation then in an arid system. How deep does that litter need to be for that layer to be formed? And so the idea of just simply taking it all off and actually composting it first and then putting it back, potentially plowing it in if you need it, these are sort of considerations that I leave to you. But now you've got material that is now at least partially decomposed, is busy with microbes, and that's all of those nutrients and the nitrogen is now in a form that is available to the soil food web to cycle onto the crop, right?
Brilliant. Brilliant. Thank you. We've got probably 6 more questions. We're going to try and rattle through these if we can. Um, I would like to see if certain liquid fertilizers are compatible with our biocomplete compost extracts. Is there specific microscopy protocol to see if these fertilizers are safe for biology? And for me, it's not just fertilizers; it could be minerals as well.
Yeah. So I've done that with just simple like lunchbox takeaway boxes. You have 3 or 5 where you're going to put your biocomplete compost, has all your different microbes, has a good assembly of bacteria, protozoa, fungi, and nematodes. And we're going to put them in the aliquots, and then you're just going to make up your fertilizer solution and treat 3 or 5 of them, and then just make a control solution, which is just water only, and treat another 5. And then you're just going to do a time trial. After 3 hours, you're going to scope them all, and then another 3 hours scope them again. And if you see a detrimental, effect on the populations of the microbes within those substrates, then it's had a detrimental effect at that concentration, right? You just need, the caveat is you need reasonably consistent compost to pull this off, because you need a compost where you count it and then you count it and you count it again, and those numbers fall within a kind of acceptable level of variability. And then we know that the effect of the fertilizer is going outside of that effect, that variability. So it's affecting it more than the variability just within the compost, right? It's definitely having a detrimental effect. And so, yeah, we need lots of replicates for that, and we need a consistent protocol. So that's how I do it. Just simple takeaway boxes. And yeah, make sure the amount of fertilizer you add is not too wet that it fills the box and, you know, makes it all anaerobic, that it's not changing the environment as much as you're seeing the effect of the fertilizer in the substrate with the microbes.
Thank you, Adam. And I've got a friend who wants to know very, very quickly what fertilizer you've done and what's the result straight away. Is there anything you can tell my friend about what fertilizer are the safest and at what rates?
Yeah, I mean, I've done lots of different seaweed extracts and fish hydrolysates and things that people would commonly use along it. I generally see when you use things with bacteria biomass, you stimulate the microbes much more. So whey seems like a good addition. You know, whey from cheese making. You get curds and whey, take the whey, mix it with the compost extract, apply it like that. That seems quite good. There was something where people put, I think they call it super labs. You can find it on YouTube. Steve Reisner. You put algae in whey and you extract phycocyanin, so you extract some of the stuff from the algae. That was really good. Um, and then, yeah, testing stuff like sulfates, like zinc
Okay.
sulfate, copper
Okay.
sulfate, because sometimes you need
Yeah.
to add trace minerals, right?
Yeah.
But you don't want to add too much. So
No.
I found something like, 4 ppm of copper sulfate in solution is kind of, that's fine, doesn't kill stuff.
Yeah.
You go
Yeah.
up to 20 ppm, yeah, you start to damage stuff, right? You start to see, a detrimental
Brilliant.
effect on the environment. So yeah, if
Brilliant.
people want to get in touch with me, my email is just like Daniel's in the comment section. It's just adam@soilecologylab.co.uk, and I can give you more specific information of, stuff I've got written down. But yeah, I've tried mainly trace elements and then seaweed extracts, hydrolysates, common natural farming inputs. Generally, where the product contains loads of bacteria, it seems to stimulate the ecology quite well.
Right.
Yeah, where it's a sulfate, if you use too much, you're gonna have a detrimental effect. But sometimes we need to use those things, so dialing it in an intelligent way is a good way to start.
Fantastic.
Also,
Thank you.
also look
I,
into the comments,
I,
because Judith has just posted. There's a very good group on Facebook, Farmate Bioferts. Have a look.
fantastic. Thank you very much, D guys. I will be sure to tell my friend. Isadora.
Yes, I'm part of that group too. God damn it. Sorry, excuse my French. Although the soil food web requires fungi, here in Vancouver Island, where humidity is near 100%, wow, and most things living just rot away due to fungal infections. Allium white rot is devastating to garlic growers here, so I have to suspect something is out of balance to a major environmental level. Peaches, for example, cannot be grown here unless under cover. How can growers rise above fungal dominance in order to grow delicate fruits, berries, and other crops?
Adam's on it. Adam's on it.
Yeah, I would say it's like this, it's building soil structure that will help, it's going to help in the same way it's going to help manage drought, it's going to help manage overabundance of water too. So the more that, if you look with your microscope and just with your eyes as you're making these composts, as they get older, as they get towards like 2 years old, they become very good at holding moisture. They can hold a lot of moisture. And in fact, if you do a kind of volumetric moisture reading of that stuff that's 2 years old, it can hold way more moisture than the stuff at the beginning of the process, say a month or 2 months old, when it looks all slimy and sloppy and you pick it up and you've got like moisture running out of it. Well, actually, when it's older, it can hold more moisture, but when you squeeze it, you can't get it out because it's being held in this microfilm on the soil particles. The soil can regulate itself better. So the only thing I have is try and build soil structure, try and build more aerobic soil structure to compensate for the high humidity and too much water.
Talk about also your courgette experiment with tweaking minerals as well.
Yeah. So there is a book by Julia Ruckledge. It's called The Better Brain. And it's just about human nutrition. And it just documents how you put broad spectrum minerals with organic molecules and you feed them to humans, and humans get better, right? If the humans have ADHD, the symptoms are less. If they have autism, the symptoms are less. If they have psychosis, the symptoms are less. If humans are stressed by earthquakes and you give them broad spectrum nutrients, they recover from the trauma of the earthquake faster, right? So broad spectrum, I took this on and I said, well, what if we couple this with the soil food web? So we put the microbes out there, but we put out broad spectrum nutrients and organic molecules to cycle based off what we see soil tests lack. Okay. So tried that. And yeah, in an environment where the plants commonly get powdery mildew every year, they get it quite quick and it affects production in this market garden. We treated it with broad spectrum minerals and organic inputs and the soil food web. And we just did one application and they got, yeah, another 3 weeks of good production. And the plants were way more resistant to the powdery mildew in the same condition, right? They live in a valley, so all the cold air drops in and it forms a dew point on the leaf. And the mildew takes advantage of this dew point to set up shop. But yeah, you put calcium into plants, cell walls get thicker, right? You keep fungi around and the calcium sticks around in the top soil. This is what you learn in the Soil Food Web course, what Elaine's experimentation has kind of proven. So yeah, coupling broad spectrum applications with the biology can really help shift kind of health problems like that. Yeah, so that's where I'd start, making sure all nutrients are sufficient, and giving the crops something to cycle. Like we were talking about before, the chitin in the ecological monograph was there to be cycled. If it wasn't there, we have limited resources, so we have to use some different tests to make sure what's there, what's lacking, and that's a good place to start.
Brilliant. Thank you, Adam. Well, we've got probably try and squeeze in another couple of questions in the 8 minutes we have left. How does using straw for straw compost affect pest population buildups versus more nitrogen-rich composts?
Yeah, I
You've
mean,
read stuff in that biomakers analysis that was quite
yeah, I
suppressed, I
mean,
would
I
say.
don't think it's a significant issue with like accumulating pathogens. So there's these microbes that are decomposers, I said before, and symbiotropic, and decomposers and pathotrophic. Generally, the longer you leave the compost, the more you see a reduction in the obligate pathogens and the obligate symbiotrophs. They need a living plant to survive. So as the composting system continues and there's no remnants of the actual plant material, the parent material that went into the composting, you select against pathogens. You also select against symbiotropic microbes, but there's microbes that blur the line and have a decompositional cycle, and they will stick around. So it generally ends up time, like 12, 13, 14 months. It generally seems to select for decomposers, saprotrophs, but you will have some symbiotropic saprotrophs around, and you will have less pathotrophic saprotrophs. But the obligate ones that are just pathogens will die back because they need a living plant to survive. So yeah, and as the compost gets more aerobic over the course of the straw composting operation, it becomes more crumbly and aerobic, and that selects against pathogens too. The fungal presence, these penicillium with all they've saved 200 million to 500 million people based on the antibiotics they produce. They also produce things that suppress viruses, suppress pathogenic bacteria, and that because they have a vested interest in protecting their host plant, they can use all this chemistry to protect the host plant if they're in the situation. So if you stop using the fungicides and you start using the fungi, you're probably going to end up with a more sustainable system. So I wouldn't worry too much about the pathogens as long as you leave the compost long enough. 12, 13, 14, 16 months or 2 years, something like that. It's going to be really good, and you're going to select against them.
Brilliant.
I'm just going to add one more tip.
Very, very quick. Very, very quickly, Daniel.
Plenty of papers that say that if you have a minimum of 4 varieties of wheat or barley or oats in one field, then you reduce your risk of disease by at least 60%.
Great. I totally agree with you on that one. Let's move on to the next question, please.
It's for the whole panel. Oh, look at that. Has anyone yet looked at the presence and significance of exclusion zone easy water as described by Gerald Pollack in biofilms and other aspects of soil biology, also including compost and derivatives?
Not got that far yet, no. But any way you can help biofilms build up in that composting, especially the nitrogen fixation in the straw compost, yeah. So play around as much as you can. Let me know if you find anything cool.
And
Brilliant.
do everything in minimum triplicates.
Brilliant. Thank you, guys. We're getting close to the end now, so we'll try and squeeze these last two in. Gosh, what a big question. How does biochar influence the soil and plants? Gosh, that's a question.
That's a question to Mick Jones.
Yeah, so we have this friend called Mick Jones. He's in Wales, and he's just been mixing biochar, small percentage, with the animal manure as it hits the sheds when they overwinter the animals. And so the animal manure accumulates, and he's spreading the biochar, and then he just takes that. I don't think he even composts it. He just spreads it. And so he's seen amazing results there. And how it seems to work is it keeps more bacterial biomass around, and that embodies nutrients. And so if his tests that I've seen are to be believed, and it would be great if I saw loads more chemistry tests on his soil, he has improved his soil in 4 years, more than you could economically do by bringing in inputs. So there's more phosphorus than you could pay for from, if you were to bring in soft rock phosphate and spread it. It wouldn't be economically feasible for him to do that, but he's increased that phosphorus. And basically, it looks like it's balanced the soil. So everything that was was excessive has gone down. Everything that was deficient has gone up. So it seems to be balancing his soil, and that's just in a pastoral environment.
Fantastic. Good. Right, let's get to the last question
Is there a way of testing or knowing how much nitrogen is being fixed from the air compared to how much was in the pile of straw before composting it?
Yeah.
Yes.
Okay,
I know.
right. So thank you.
You just have to weigh everything. I bought a ton scale and I just hang it from a telehandler, and we lifted 3 bales of straw separately. We got the weight of the straw. We got the size of the Heston bale, the big 8-foot Heston bales, and then we judged the depletion of the volume over 13 months to be 50%. Realistically, it was closer to 60% remaining, but we just assumed it was 50%, and then we took samples of that. And then we packed it into 1-liter containers. We weighed that. So we basically measured and weighed everything as much as we could, plugged it into a spreadsheet. Frida did that work. I went through, I have to admit, an absolute emotional roller coaster when I got the first results, because starting nitrogen, 0.5%. In that compost, it was 2.5%. I was like, what? 5 times more. But then Frida weighed everything, measured everything, and we got that doubling.
Brilliant. Thank you, Daniel. Thank you, Adam, for that. Absolutely amazing. Really appreciate.
I'm looking forward to this one. Before you say anything, I'm really looking forward to this one, because Joe, we were there.
Just hang on, Daniel. Just hang on 1 minute, please. We really appreciate your time, guys, today for the first webinar in this 5-webinar series. And 6th of November, 9 a.m. Pacific time, we have got Todd, the amazing Todd, Vivian, and Joe talking about practices across landscapes. So please, please, please stay tuned for that one and join us for webinar 2. Remember, you can watch webinar 1 again on YouTube. It'll be available. on our YouTube channel. And please connect to us on LinkedIn, follow us on Instagram, like us on Facebook, subscribe on YouTube, and follow us on TikTok. Isadora, Adam, Daniel, and the team behind the scenes, it's been a fantastic workshop. Thank you all, and thank you all for your amazing questions. And have a lovely rest of the evening, and we'll see you next time. Thank you all.
Cheers, guys.
Thanks,
Bye.
guys. Thanks for having us.